What is a chiral molecule? When determining the chirality of any object, we need to consider about the mirror images of this object. Now, if the mirror images are non-superimposable, or in other words, if those are not aligning with each other, just like two hands or two hand gloves, those images or those mirror images are known as chiral. On the other hand, if an object's mirror images are aligning well with each other or superimposable with each other, we call them as achiral objects. Now, in this lecture, we will identify in any given organic molecule uh, whether it is a chiral molecule or achiral molecule or any given carbon atom as chiral carbon atoms or achiral carbon atoms. And also we will learn what are the Fisher projections and how to identify the different forms of these chiral molecules called D and L enantiomers. Before go in depth, we will see what are these chiral molecules and where does it applies. Now, we have learned about isomers. Now, these isomers are the molecules which have same molecular formula. Now, we can divide these isomers into two classes. The first one is the structural isomers. And structural isomers are the compounds that have same molecular formula but different connectivities. For example, if you take C2H6O molecular formula, we can draw different structures by connecting the atoms in different ways. One example is ethanol. And the second example is dimethyl ether. Now, both of these molecules have the same molecular formula, which is C2H6O, but if you look at the atom connectivity, those are different. So that is an example for a structural isomer. And propanol and propanone are also structural isomers. Now, if we look at the other class of isomers, that is the stereoisomers. Now, these stereoisomers have the same connectivity of atoms, but their spatial arrangement is different. So those are known as stereoisomers. There are multiple classes of stereoisomers, but I'm just going to focus on one of the stereoisomers called enantiomers. Now, enantiomers are what we are interested in this chapter, and another name for enantiomers is non-superimposable mirror images. Now, as I mentioned before, these chiral molecules have mirror images which are not superimposed with each other. So those are called as enantiomers. When it comes for chirality, this identification of a chiral molecule is very important and an expected core chemistry skill in this class. Now, as I mentioned, our two hands are non-superimposable because the mirror image, if we take the mirror image of one of our hands, these mirror images are not aligning with each other. So that's an example how to identify a chiral object. Now, if we look at some other examples, as I mentioned before, these hand gloves are chiral because the mirror images are not aligning with each other. Or an empty glass will be achiral because its mirror image can be superimposed with each other. And if you take a pair of shoes, those are chiral because they are not aligning with each other or they cannot superimpose with each other. Um, so this is how the chirality and achirality can be identified. We are interested on chiral carbon atoms in organic compounds. When it comes for organic compounds, how can you identify a carbon atom is chiral or not? Now, this is identified by checking for the different atoms or groups attached to the carbon atom. If a carbon atom contains four different atoms or groups, we call them as chiral carbon atoms. Um, and in this case, if the molecule is chiral or if that carbon atom is chiral, um, those are not superimposable. And such compounds are called enantiomers because these compounds are not superimposable with each other. That is one type of stereoisomers. Now, for example, this mirror image of this chiral molecule are enantiomers. These two are enantiomers because we can't superimpose them with each other or we cannot align them with each other. Just like you see here, it's not possible to superimpose on each other. But if we look at an achiral carbon atom, an achiral carbon atom is the one that has two or more than two identical groups or atoms attached. Now this carbon atom here, the central carbon atom here is achiral because there are two bromine atoms attached which are the same type of atoms and chlorine and hydrogen. Why we call this as an achiral? So if we take the mirror image of this molecule, which is this one, now we need to check, can we superimpose these two? It looks like it's not, but we can rotate this molecule. If we rotate this molecule, it will end up with this conformation, right? Now, if you look at this one and this one, those two are the same. So by rotating, we can get the same molecule. So this is true for any achiral molecule. Now let's do a learning check. In these two compounds, indicate whether the carbon in red is chiral or achiral. Now in this molecule, how do we check this? We just need to check the connectivities, the four connectivities for this carbon atom and whether those groups are the same or different. Now for A, if we look at this carbon, there is a hydroxyl group, a hydrogen atom, and CH2OH group in this side and a CH2OH in this side. Okay, now we see same groups on side by side. If there are same groups, then it is not chiral. We call it as achiral. It has to have four different groups in order for it to be chiral. Now, if we take this carbon, now this group is attached there, so that is one group, and NH2 is one group, hydrogen is one group, and carboxylic group COOH is another group. That means there are four different types of groups. Now this is chiral. So this is how we can determine whether a carbon atom is chiral or not, and it's very simple. It's very simple. You just have to check which type of atoms or groups are attached to the given carbon atom. Okay. Now, in order to simplify these three-dimensional molecules, there is a model called Fischer projections. Now, what is this Fischer projection? This Fisher projection is a two-dimensional representation of a 3D molecule. So it's actually a simplification. Now, in any given molecule, we can, for any given carbohydrate molecule specifically, we can draw a Fisher projection by placing the most oxidized group. The most oxidized group can be the ketone group or aldehyde group at the top. And then uses vertical lines for bonds that go back and horizontal lines for bonds that go forward. So usually this aldehyde group is placed on top. And the intersections always have usually like chiral carbon atoms. Okay. And here they can have different groups, maybe hydrogen atoms or hydroxyl groups. And we can identify some other groups like CH2OH. So this type of representation is known as a Fisher projection. We'll see an example, a very simple example. So this is the glyceraldehyde molecule. Glyceraldehyde is this carbohydrate with 3 carbon atoms, one of the simplest carbohydrate. Now, if we look at the first, we'll see this carbon atom. Now, this is a chiral molecule because this carbon atom has four different types of groups attached. Now, we can represent this same 3D molecule in Fisher projection. So this is the Fisher projection of the same molecule. Now, how can you convert this into a Fisher projection? Now, as I mentioned before, you need to keep the aldehyde on top and this carbon is in this intersection and the atoms that comes forward. Now, this is a dash wedge structure. Okay, dash wedge structure is given here because these dashes represents the bonds that goes backward and the wedges represent the bonds that comes forward. The bonds that comes forward is represented by this horizontal line and the bonds that goes backward are represented by the vertical lines. So that's how the Fisher projection comes, and you can draw a similar Fisher projection for the other enantiomer. So these two are enantiomers. Those are mirror images of a chiral molecule. Okay,